Hello. I can't see anything, so I'm just going to start. As it's traditional, you put a slide up to say about who you are. My name is Gerald Benischke. I remember Java 1.0 even. That should tell you about how long I've been in this industry. I've not started in the security space. I fell into the security space after doing about 20 years of development at different places, HMRC, money supermarkets, banks. It gets more boring the further back you go. So I've described myself here as a maker of software, and more recently, I'm a breaker of software. I also wear many hats. Now, one of the best stories that a friend of mine told me once, he used to work in a bank as a sysadmin, as they then used to still be called. I guess nowadays he would be a DevSecOps engineer manager. Anyway, he told me about this cabinet that he found in the server room, and there was a router hanging in midair, suspended by the two cables. And he sort of asked, well, why is that? Why can't we fix that? So it's like, no, we can't fix that because it's a critical part of the infrastructure. And it was literally held together by gaffer tape. And I think that's a great metaphor of the state of software engineering sometimes. You find things that are just bolted together that then kind of have unintentional impacts. So I've, in the last 2 years, moved into AppSec with my developer hat on, with my DBA hat on, with my architect hat on, because I kept finding issues. And eventually I found so many issues that they told me, well, why don't you do that full time? And I've been enjoying myself ever since. So in this talk, I'm not going to talk about distributed denial of service attacks. I'm not going to be talking about the low orbit ion cannon that overwhelms you with brute force and ignorance. I'm talking about targeted precision strikes. I'm going to be talking about a bit about the play framework and the vulnerability that I found last year to illustrate how modern infrastructure can amplify attacks. And I've thrown in a few other interesting examples. So let's begin. Right, in the previous slide, I cleverly mentioned the low orbit ion cannon, which is so often used in DDoS attacks, but obviously the name comes from Star Wars, so more Star Wars references. Let's stick with that. A distributed denial of service attack is kind of like the Imperial fleet with its lumbering Star Destroyers coming along and shooting everything in sight and not hitting anything. And a plain denial of service attack is your friendly neighborhood band of rebels that pilot their X-Wings and take out a Death Star with a single shot. So, still, distributed denial of service. Now, this is the last bit of my Star Wars metaphor, I promise. I want to talk a little bit about the architecture of modern systems, where you have content delivery networks sat in front of web application firewalls, sat in front of load balancers before you hit that application that your software developers have put together. And then there might be a database behind it, but that probably is prone to SQL injection, but we're not going to talk about that today. So effectively, in order to get your attack to the intended target, you have to navigate that trench, get to the exhaust port unharmed before you can do any real damage. And I think this is why DDoS, the distributed denial of service, is often very inefficient because it has to navigate that trench. It has to get past the CDN, the WAF, all the rate limits, DDoS protections that are put in front of it. It's brute force and ignorance. So, my specific example, and I intentionally made that really small to read, is about a vulnerability that I found. It's deceptively simple payload that can do serious damage. So what you can see here is a bit of JSON. Looks a bit strange, but it's still JSON. It's just an object with a field called X, which then has an array that contains an array, that contains an array, that contains an array, with a single element in it. Now, if you do the square brackets 30,000 times, and then the closing square brackets 30,000 times, you have got a payload that is valid JSON, but in the play framework, which I was working with, it would cause an out-of-memory error. Because essentially what would happen is that it would go and try to parse this and turn it into something else. And while it was going through the nested and the nested and the nested objects, it just fell over. Now, what I've done here is after it ran out of memory, the application just shut down, because it's a reasonable thing to do in these days with the infrastructure, because something shuts down. Usually what happens is that you've got things that bring it back up again. Anyway, so the application stopped, and it would return a HTTP status 503. That single request can bring down a single server, but there's more. It's something that I call an automatic amplification. Like I explained before, you have those load balancers that sit in front of it, and as it happened, after I took the vulnerability out of my local testing and tried it out on a test system, it wasn't one instance that failed, it was 3 instances, and that was, at the beginning, a bit of a head-scratcher. So I looked at it and found that instead of the proxies, the load balancers that were sitting in front of the application would take that 503 and say, oh, something must have obviously gone wrong. I'll best route that request to another instance, which then reacts in the same way. And then another one, which blew up as well. So one request can blow up 3 instances. I think that could be pretty serious. So will the infrastructure that we've so patiently built to host all of our applications save us? You know, we've got self-healing, we've got auto-scaling groups, we've got automatic restarts. That's all well and good, but most of the time these things take a little time. It takes a little time for the platform to realize that something has gone wrong and that the instance needs to be restarted. It takes a little time for the instance to come up. And this little snippet of bash script essentially sends 50 of those requests, leaving 10 seconds between each of them. And if each of those take out 3 instances within a couple of minutes, whose infrastructure would still be alive? So I guess the moral of the story is here, ask yourself, how quickly can your self-heal actually self-heal? Would it survive if 3, 6, 10 instances suddenly disappeared? Pardon me. That's exactly what happens when one of those attacks hits. So effectively, what you're going to end up doing is playing a game of whack-a-mole. A single request can take out 3 instances, instances disappear, and the interesting thing is, well, what if that is a crucial bit of your infrastructure? What if somebody was to take out your authorization service for an hour. Well, nothing would get done. And you don't need millions of requests and billions of bytes of traffic to do it. That's what I mean by precision munition. But would a WAF save us? Would a web application firewall save us? Well, actually, no, it won't. Because while they sit in front of vulnerable resources, they're good against abnormal requests, they're good against known patterns. So effectively, it's an arms race between attackers and defenders. But this particular attack, I think, presents a problem, because typically, web application firewalls only examine the first 8 or 16 kilobytes of a payload, because essentially these things take resources, and if the WAF was to examine the whole payload, it would be too expensive for AWS or Google or Azure. So in my example, the play framework by default allows payloads up to 100 kilobytes. Now I've got my 30,000 open square brackets, my 30,000 closed square brackets, so that's about 60 kilobytes. So I could stick something at the front of my JSON payload that is an innocuous looking very long string that fills up the 8 or 16 kilobytes that the WAF will inspect. And the rest of the payload would be passed through and would then blow up our poor application. Now, will SCA, will software components analysis, will the dependency scanners save us? Now, this particular vulnerability ended up getting a CVE number. It ended up getting a score of 7.5, because that is the biggest score that a denial of service can get, because it's not remote code execution. And the dependency has been mitigated. Now, so the question is, obviously if a dependency scanner like SNCC or Sonatype or X-Ray or even the OWASP dependency scanner will show you that. But who here, now this is going to be interesting because I can't see any of you, who here looks at all CVEs with a score of 7.5? Yeah, that's what I thought. So the problem here is that the dependency analysis will give us all the 9.8 scores, and we'll very quickly look at that. But when you think about it, a denial of service that can take out your whole website with a few requests, I think that warrants a little bit of attention. Now, this is not the only way of doing this. Another fun way that I found was to use something called hash collisions. And essentially what you've got is a list of elements. Here we've got an XML payload, and all these strings have got the same hash code, which means that the XML parser, when it's parsing it, it tries to put it into a map. A map is a sort of dictionary data structure that is optimized for fast lookup. But when all of these have got the same hash code, it's not an efficient data structure because they all get put in the same bucket. And if the payload is large enough, then the code will get slower and slower and slower. And I tried this out, and I found that just 10 concurrent requests were able to take a few instances and eat up all the CPU. And if you sustain this long enough, the whole service will be starved of CPU, and then your instance will be destroyed and restarted. But what if I keep sending requests? Again, I don't need brute force to do a lot of damage. Other examples are YAML bombs, regular expression denial of service attacks, the infamous XML billion laughs attack or zip bombs. All of these tend to be designed to abuse the processing and essentially break something. The interesting thing about those is if we take this regular expression DOS denial of service attack vector, I found a vulnerability and it had a CVSS score of 5.3, I think. It was very low down, and very often people use the dependency scanners to go and have a look at, let's find everything that has got scores of 8 or above, and we need to mitigate that within 48 hours. Interesting story, I actually ended up looking at all of the CVEs that were on our estate and found that 90% of them, even the ones with the scores 9.8, were actually not applicable. They could only be used in a certain scenario, and fixing the dependency and vulnerability will have added nothing to make you more secure. So, the other big problem is, usually, we work at scale. It's easy to secure 20 microservices. It's easy to keep 50 different code bases in your head. But when you get to more complex systems, like this badly drawn diagram of services that interact with each other, what if you have 1,000 microservices? What if you have 4,000 repositories? How many CVEs do you have? Is it still realistic to go and, oh, we'll just fix all of them? Well, the first time I fired up the dependency scanner, 836,486 reports. CVEs, by the way, you might be able to tell that the CVE scores are one of my pet hates, because all those lovely vulnerabilities that don't end up with a remote code execution, they get a score of 7.5 at the most, and a lot of people look at that and say it's a severity score. It's not a risk score, it's a severity score. What the potential is for it to happen, what the risk is, depends entirely on context. And that, to me, means that you're actually gonna have to look at all of them. You know, that DDoS vulnerability, CVS score of 5.3. Well, I'm going to take a step now to what can you do about it. Now, I'm going to briefly talk about the paved roads, the golden path approach. Now, this is the idea that if you have a reasonably complex system, if you opinionate it about it and sort of say, well, we don't want every different team to implement things in their own way, using their own frameworks, then you might actually have a chance to generalize and think about things at scale. You can kind of go, well, I know these are the patterns that we follow, and I know when I look at all the vulnerabilities, they're all going to have the same vulnerabilities, which means that I can reason about them in a sort of generic way. So what I did on that terrible user interface that gave me 800,000 reports, we built a very rudimentary vulnerability curation pipeline. So essentially, we took the vulnerabilities and I wrote, because after all I'm a software engineer, I wrote a script, I turned it into Google Sheets and I drew pretty pictures with it. That allowed me to take those 800,000 reports down to finding about what are now probably about 800 different CVEs that needed to be looked at, that needed to be evaluated, that needed to be put in context, that allowed me as a sort of AppSec snooper to find out how many of those do the service teams really need to pay attention to. Now, it's really important for me to sort of mention the fact that application security, or InfoSec as a whole, doesn't exist in isolation. It's not sat in its ivory tower that only comes down with the big no at the end of a software development lifecycle to say, you did this wrong. It's really important that security works with development. It's that cliched buzzword bingo, shift left. You want to be able to have a conversation about the development before everything, the code has been written, before it's been tested and signed off and somebody said, yes, we can put it into production. Service teams, the ones that are writing the code, are often in a position where they just don't have the time to look at every single bit of security. They don't have the time because the business says, oh, we need this feature and we need the next feature. They become feature factories. And when time is in short supply, then sometimes shortcuts are taken. Like I said before, security teams can't be in that ivory tower because one of the things that is really important is that things need to be put into context. Things need to be understood, because if you don't understand how a vulnerability could be exploited and how it could be exploited on your system, then you don't really know whether something is a problem or not. And I'm a firm believer that we should not pay too much attention to the scores, because it doesn't really matter, because you can get really serious stuff at the low end of the scores, and you can get stuff that you can ignore at the high end. The key is to share context, to collaborate. So, because I'm not a sadist and I won't want to keep you from the bar, I'm nearing the end here. So the lessons for me about denial of service is that we need to take it seriously. If you think back to this, a single request can take down 3 instances of a service. If there's one service that is really crucial, that every other service depends on, like, the user interface for logging into your estate, that can have serious consequences. It's also very difficult to find some of these attacks and to protect against these attacks. What I think you need to do is to sort of take the approach that you can manage the scale, that you can curate all those vulnerabilities, that work hand in hand with the teams that are actually delivering the services, and that you use a sort of multiple layers of defense. And questions?